Okay, so get ready, because today we're taking a deep dive into something truly mind-bending, something that might just rewrite the rules of the cosmos, at least when it comes to those enigmatic things, black holes.
You're not kidding, and it all starts with this fascinating research paper, one that really makes you think about what we think we know about gravity.
It's this whole bumblebee gravity idea, right?
Exactly. Have you ever, felt like the laws of physics are a little too perfect, like maybe a bit too neat and tidy?
You mean like they're holding back the universe from getting a little wild? I like where you're going with this.
That's the thing. Right at the core of a lot of physics is this assumption, a principle called Lorentz symmetry.
Okay, you got to break that down for me.
So basically it says that physics, operates the same way everywhere, no matter your speed or direction.
So gravity works the same on a merry-go-round as it does standing still, that kind of thing.
Exactly. A bit simplified, but you've got the idea. But this research paper, it explores whether this fundamental symmetry, this Lorentz thing, it might actually break down.
Break down how?
Well, at extreme scales, we're talking about places where gravity is just cranked up to 11.
Black holes, you've got to be kidding me.
You got it. Black holes. That's where bumblebee gravity comes into play.
Okay, I'll admit, the name alone, I was hooked. But seriously, how does gravity actually change near a black hole with this bumblebee gravity thing happening?
Well, imagine kind of like a field, an invisible energy all throughout space-time. That's the theoretical bumblebee field.
Okay, I'm picturing it like an invisible force field around a black hole.
Yeah, you're getting warmer. So near black holes where gravity is just insanely strong, this bumblebee field, it gets strong too.
Yeah.
And it starts to, mess with how gravity normally works.
Messing with gravity, now that's my kind of science. So does that mean there's like a different kind of black hole out there, like a bumblebee version?
Now you're thinking like a physicist. This theory, it actually does predict a whole new type of black hole, one that behaves a bit differently.
Okay, now you have to tell me more. How do we even begin to study these bumblebee black holes? Do we, put a giant telescope up to one?
If only it were that easy. This is where a research paper comes in. It dives into a specific type of black hole predicted by this theory.
Okay, walk me through it. What makes them different, these bumblebee black holes?
Hold on. Before we get lost in the weeds with all the technical jargon, let's talk about how we could actually observe these bumblebee black holes. How do we even know they're out there?
Yeah, good point.
The paper uses two main things, two pieces of evidence: black hole shadows and something called, get ready for it, quasi-periodic oscillations.
Black hole shadows. Wait, are we talking about actually seeing a black hole? I thought they were invisible.
You're right. Light can't escape a black hole's gravity, so we can't, directly see it. No.
What are we talking about?
Think of it this way. Imagine a black hole passing in front of a really bright background, like a giant cosmic spotlight.
Okay, I'm picturing it.
What we'd see isn't the black hole itself, but the shape of that missing light. It'd be like a silhouette.
That's the shadow.
Exactly, the black hole shadow. And here's where it gets interesting. This paper proposes that the size of this shadow, it can actually change.
Change? You mean grow or shrink?
Yep. And that change, it all depends on the strength of this bumblebee effect, how much that Lorentz symmetry is actually being messed with.
So by studying these shadows, by seeing how they change, we could figure out if a black hole is one of these bumblebee black holes.
In theory, you absolutely could. But in astrophysics, right, there's a catch.
There's always a catch. Lay it on me.
So the paper, it found that for some values of this bumblebee effect, for certain strengths, the shadow, it would look exactly the same as a regular black hole's shadow.
So we wouldn't be able to tell them apart.
Not just by the shadow alone, no. It's like trying to tell twins apart when they're wearing the exact same outfit.
Frustrating. So if shadows aren't enough, how do we find these bumblebee black holes?
That, my friend, is where those quasi-periodic oscillations I mentioned come in. And trust me, they're even cooler than they sound.
Okay, you've definitely piqued my curiosity now. What in the universe are quasi-periodic oscillations?
All right, buckle up. We're about to go even deeper into the weird and wonderful world of black holes.
Quasi-periodic oscillations. Okay, I'm going to be honest with you. That sounds a little intimidating, even for a deep dive like this.
Laughing. Don't worry, they're not as complicated as they sound. We can call them QPOs for short. But to really understand them, we need to shift gears a bit. Instead of those supermassive black holes at the centers of galaxies, we're going to zoom in on their smaller cousins.
Smaller black holes? Are we talking about those tiny ones that Hawking radiation is always messing with?
Not quite those. Those are even smaller, more like theoretical.
Mm.
We're talking about microquasars. Think of them like black holes in miniature, still incredibly dense, still with that intense gravity, but on a smaller scale.
Okay, I'm picturing a black hole, but like
Well,
pocket-sized.
chuckles. Well, not quite pocket size. They're still many times the mass of our sun, but you get the idea. And even though they're smaller, they still pull in the matter around them, just like their supermassive counterparts.
And that's where things get interesting, right? Because it's that infalling matter that gives us a way to actually observe these black holes, these microquasars. It's like their cosmic dinner announcement.
You got it. As all that matter spirals inward toward the microquasar, it heats up like ridiculously hot and starts emitting X-rays. And those X-rays, they create this kind of cosmic light show.
Okay, now we're talking. So what do these QPOs have to do with this incredible light show?
Here's the thing. That light show isn't constant. It's not just a steady beam. It actually flickers. And those flickers, they happen in a pattern that's the quasi-periodic part, and those are our QPOs.
Whoa, hold on. So these black holes, these microquasars, they're like blinking at us. And the pattern of that blinking is what tells us about this bumblebee effect.
You're getting it. Now, this research, what they did was incredible. They took that idea that those QPOs, those flickering patterns, they could be affected by this bumblebee effect.
So they could be different for bumblebee black holes than for regular black holes.
Exactly. It's like, imagine you're listening to a song, a familiar tune, but the tempo is slightly off. That difference, that's what we're looking for with these QPOs.
Okay, that is seriously cool. But how do we even begin to measure something like that? Are we talking about like timing the blinks of a black hole?
You're not far off. These researchers, they didn't just theorize about it. They got their hands dirty with some real-world observations.
Okay, tell me they pointed a giant telescope at a flickering black hole and hoped for the best.
Chuckles. Well, it's a bit more complicated than that, but essentially, yes, they focused on two specific microquasars, and get ready for these names because they sound like something straight out of Star Trek GRO J165540 and XTE J1550 564.
And GOJ say that 5 times fast.
Right. I told you they sounded like something from Star Trek. But anyway, what they did was they took the data, the actual observed flickering patterns, the QPOs from these two microquasars, and they ran the numbers.
They were looking for those subtle shifts in the rhythm, right? Like that slightly off tempo you were talking about.
Precisely. They compared what a regular black hole's QPOs should look like, according to our current understanding of physics, to what these bumblebee black holes might sound like if this bumblebee gravity idea is correct. And what they found, well, it's pretty amazing.
Okay, you can't leave me hanging like this. Did they find those off-tempo black holes? Was the rhythm a little funky?
All right, I won't keep you in suspense any longer. They found that when they factored in a bit of this bumblebee effect, when they allowed for the possibility that gravity might be a little different near these microquasars, well, the math worked out.
Are you serious? You're telling me that these observations actually fit the bumblebee black hole idea better than our regular old vanilla black holes?
It's still very early days, mind you, and a lot more research needs to be done. But the implications of this, the possibility that we might actually be seeing evidence of this bumblebee effect, of a fundamental shift in how gravity operates in these extreme environments, well, it's incredibly exciting.
So we're saying that to really test the limits of physics, we need to look at these extreme environments, these places where gravity is just playing by a whole different set of rules.
That's what's so tantalizing about black holes. They really push our understanding of how the universe works. And these microquasars, they're like little windows into those extreme environments.
It's like each one of these microquasars is a little physics experiment just waiting to be observed.
Exactly. And the more we observe, the more data we gather, the clearer the picture becomes, and who knows what we might find. This study, it focused on just two microquasars, right?
2 out of how many in the entire universe? That's just a drop in the cosmic ocean. So what happens when we start looking at more of them? What could we learn from a whole symphony of these flickering black holes?
Now you're asking the big questions. That's what's so exciting about this kind of research. It opens up these entirely new avenues for exploration.
So instead of just 2 data points, 2 little glimpses into bumblebee gravity, we could start to build a more complete picture. Like, does this bumblebee effect, does it change depending on the black hole? Is it stronger around bigger ones or ones that are feeding more actively?
Exactly. Or what if it changes over time? We could even start to map out this bumblebee field, see if it has like an edge, a boundary where its influence starts to fade.
Oh, like mapping out a cosmic force field. Now that is an image.
It's like having a new set of lenses to look at the universe, one that lets us see these subtle variations in gravity that we could only dream of before.
I have to say, this whole idea, even if it turns out that this specific bumblebee theory isn't quite right, the very fact that it's even possible, that gravity itself might have these hidden depths, it's incredible.
It's a humbling thought, isn't it? It reminds us that for all we've learned about the universe, there's still so much more out there, waiting to be discovered, mysteries that challenge our assumptions about how reality itself works.
Maybe the rule book of the universe is a little more flexible than we thought, with room for addendums and footnotes and maybe even a whole secret chapter on bumblebee gravity.
And who knows what amazing new insights those secret chapters might hold. That's the beauty of science. It's not about being right or wrong. It's about following the evidence wherever it leads, even if it leads us to a whole new understanding of gravity and black holes and the very fabric of the cosmos.
And sometimes, those unexpected detours are the ones that lead to the most breathtaking discoveries. Well, that's another deep dive into the world of astrophysics for us, and I have to say, this one has left me with more questions than answers, but in the best way possible. So until next time, keep looking up, and remember, the universe is full of surprises, so keep an open mind. And maybe, just maybe, you'll hear that faint buzz of bumblebee gravity out there in the cosmic void.